I'll go ahead and hit record here. So today we're talking about these Taylor and Maclaurin series. So again, the idea here is that we're trying to copy as much information about some function at a particular point. So we want to get the height right. We want to get the slope right. We want to get the concavity right. And if you just keep on going down this path, right, you want to get, right, concavity has something to do with the second degree or the second derivative. Maybe you want to get the third derivative correct, right? The physics term for that is like the jerk. So right, it goes velocity, acceleration, and then jerk. Maybe you want to get the fourth derivative correct, and the fifth derivative, and all this sort of stuff. Get as much information as possible into your polynomial. You'll need a higher and higher degree, but this is the idea behind the Maclaurin polynomial here. And so in general, if you would like to have it centered at A, so we centered ours at 0, and that's the Maclaurin series, or if you stop at some point, that's the Maclaurin polynomial. In general, though, if you want to center at something else, maybe you don't want to center it about 0, maybe you want to center it at 1 or 5 or something like this. This is the idea behind a Taylor polynomial. So Taylor comes a bit later, but gives a more general formula for this. So in general, if you would like to have a Taylor series, right? Again, these are going to be very similar to our power series. They are infinite polynomials here. We're centering it about A, right? Then again, you're going to be copying in a lot of derivative information here, right? So we're going to be copying a lot of derivative information. Of course, you do need to offset this because if you were to take all those derivatives, right, a bunch of exponents would come down, right? We have this that has x's in it. And if you took all those derivatives, right, maybe this is raised to the 5th power or something like that. And if you took 5 derivatives, a 5 would come down, you'd reduce your power by 1. Then a 4 would come down, you'd reduce your power by 1. Then a 3 would come down, you reduce your power by 1, and you'd keep on doing that, right? And so in order to cancel all those out, right, the 5, 4, 3, 2, 1, all being multiplied together, that's why you need this n factorial right here. So it's just kind of to counteract the derivative to some extent. Of course, the special case, like I just mentioned before, if you have centered about 0, you call these a Maclaurin series. So that's really the goal for today, is upgrading our information about power series. Last time we said we're going to figure out as much as we can do with 1 over 1 minus u, right? And we got pretty far. There's a lot of things that you can do, quite surprisingly. But still, there's some functions, right? No matter how hard you try, you're not going to be able to write them as 1 over 1 minus u, even if you take derivatives and integrals and all that sort of stuff. So this is getting into like this bit here, right? No matter how hard you try, you're not going to be able to write e to the x as 1 over 1 minus u, some reciprocal function. And so that knows that, 11.9 technique that we came up for power series won't work for e to the x. And so you do have to do something a little bit different, and that's kind of where the Maclaurin and the Taylor series comes in.
Do they need to remember all this theories?
So you should double check on the formula sheet for the exam, right? The formula sheet has quite a bit of these, and I believe the same portion for the formula sheet is being put on the next quiz that covers the 11.10. So I don't think it's all of these, but quite a few of them, yes, are included on the formula sheet. Good. And of course, so we'll have lots of examples. We did some in the pre-class videos, and we'll do a lot more in today's class as well. Yes, I would recommend watching the 11.11 video for Friday, please. And someone asked about Fourier series. Yeah, it's a different type of series where instead of polynomials, you have sines and cosines. And so those are nice, but a little bit more complicated than the ones that we're doing here. Okay, so let's go ahead and get into our problems for today. Oops. This is, I believe, I copied this from the formula sheet right here. So these are all the ones that we have. And likewise, I said that these will be given on the quiz as well for you to use as needed. So these will be available to you. And so I'd like to kind of order today's lesson, in terms of difficulty, right? Maybe kind of back in the, like 5.4 or so, I said level 1, level 2, level 3, right? And things got more difficult as time went. And so I want to do something similar here. where first off, using these, we can figure out many other Maclaurin series or polynomials just by using these directly. Similar to this whole 1 over 1 minus x sort of deal. We just do some substitution, right? We write this in terms of u, and then we substitute something in. And so we can actually create quite a lot just from these directly. So for instance, if I wanted to find the Maclaurin series, and we'll write this in sigma notation, for x times e to the x. So notice when it says Maclaurin series, it means that it's going to be centered about 0. All of these things are centered about 0, right? Because you don't have like x minus 1 to the n or something like this. This would be centered about 1. You have x to the n, or you could write that as x minus 0. So these are Maclaurin series because they're all centered about 0 here. So we want to find the Maclaurin series for x e to the x. And so in order to come up with this, well, we know already the infinite polynomial, the power series, the Maclaurin series, lots of different ways of saying the same thing here, of e to the x. And so if I would like x e to the x, well, this is just going to be equal to x times, and again, I go and I find my e to the x, and this is the sum from n equals 0 to infinity of x to the n divided by n factorial. And so if you'd like to find a Maclaurin series, well, generally when we're doing power series, right, we like to combine all of our coefficients into one piece and all of our variables into one piece. So I'm going to go ahead and write this, pushing that x inside of the sum here. I think the easiest way to write this would be, I'm going to do the 1 over n factorial. That's all the coefficient stuff. And then all the variable stuff, well, let's see, we have x to the n, and then we have this one more x that we need to multiply through by. And so I'm going to write it as x to the n plus first power. And so this right here would be the simplest way to write a power series for this. Of course, if you have some reason why it needs to be, you need to figure out the coefficients in front of x to the n, right? You could re-index and get your x to the n's if you would like. Now, moreover, right, it asks to state the radius of convergence. Well, just like before, right, when we use this 1 over 1 minus x business a lot, remember we used the radius of convergence 1, and we had to maybe make some alterations to that if we did some substitution or whatnot. The same thing is going to be true for all of these, is that you can use the radius of convergence for the power series or the Maclaurin series here. So in this case, the radius of convergence is infinity. And multiplying by x is not going to change that. Remember, if you do some substitution or whatnot, you do have to kind of convert from u's to x's. But here we never did a u substitution or anything. So the radius of convergence is just going to be infinite. So this will converge everywhere, kind of similar to what we did in the graph before class. Okay, so you can see that if it lines up fairly well with this table up above here, that you can just use from that. And these are pretty darn fast. Let's go ahead and do this one here. Sine of 3x squared. Well, we know from this table here, sine of x. And, similar to the 1 over 1 minus x sort of business, it may be good to write this in terms of like u or something like that. So instead of xu, because then you can kind of more directly think about what you would want to substitute in here. So I would like to use this here, where my u is going to be equal to 3x squared. So I'm going to go ahead and substitute that in everywhere I see my u. So again, sine of 3x squared is going to be equal to the sum from n equals 0 and beyond. And you just have to make sure that we copy these down correctly, right? So we have this alternating piece, and then we have all of the odd powers, right? So an alternating piece and all of the odd powers. So -1 to the n, and then we have u to the 2n plus 1. And remember, my u is 3x squared. So let me go ahead and substitute that in there. 3x squared to the 2n plus 1 divided by 2n plus 1 factorial. Now, my final answer, again, I'm going to group together all of the powers of x and all of the coefficients. This is a good habit to be in, especially for like web work and things like this. So let's see, all of the x stuff. Well, the only x stuff is this x squared, and then I raise it to yet another exponent, right? So I have x squared, and then I'm raising that to the 2n plus 1. So this is going to be x, and remember these are going to multiply. So this is going to be 4n plus 2. It's going to be the power of x there. All of the other stuff doesn't have any x's, right? This is going to be the coefficients. So we have this alternating piece. We have this 3 that was also being raised to the 2n plus 1. So don't forget about that. And then we have this denominator, this 2n plus 1 factorial. So this is all coefficient work, right? This would be our c sub n's, or really c sub 4n plus 2, I suppose. Those are the coefficients next to the x to the 4n plus 2 power. So those are all coefficients, and this is our powers of x. And just as before, right, we had a radius of convergence of infinity for sine. And so here my u, we can take, really infinitely many steps away from the origin, or x equals 0, or u equals 0 in this case. And so if we substitute in our specific u, 3x squared, well, we can divide by 3. And we can take the square root. And notice that it's pretty hard to get this off of infinity. And so the radius of convergence here is going to be infinite. So here would be my final answer as far as a power series that represents this particular piece. And then here would be my radius of convergence. All right. Any questions on this so far? Looks like Blake, you have a question. You have the floor.
Yeah, I was just wondering for like the examples above, where the radius is equal to infinity.
Yes.
Would you I can't think of anything that would change that. Would it always just be infinity? Like I know that if the radius is 1, something could change that, but
yeah, it's really hard unless if you were asked to use one of those to create a even that wouldn't do it. Like I was thinking about a very strange power series to make.
Yeah.
But no, yeah, it's really hard to get that off of infinity.
Okay. So the only thing that would really change is like natural log 1 plus x or 1 over 1 minus x.
Yeah, these ones with a radius of convergence of 1. Yeah.
All right.
They could
Appreciate
possibly
it.
change. Yeah, definitely. Let's do a couple more problems here, and then we'll take some more questions. These are very similar to the ones above, except for instead of the series, it just wants a polynomial. So here, the Maclaurin polynomial of degree 5. So we're going to stop after 5 terms here, or I guess including the 0 term. So really 6 terms. And so, okay, but again, it's going to be very similar to up above. So here we have the natural log of 1 plus, I'm going to go ahead and write this, put a u there. And again, we can see that we want our u to be equal to negative 2x. And so, okay, well, we can go ahead and kind of copy in here. Again, it has this alternating piece. It starts at 1 here. And then we're just dividing by n in this case. So let me go ahead and hopefully I can write this down correctly. So n equals 1 to infinity, this alternating piece offset by 1. And then we have our u, which is negative 2x, u to the n divided by n. And this is, well, if you wanted to have the series, but of course we only want the degree 5 polynomial. So I'm going to go ahead and just start writing these things out. Won't go on forever, but we only care up through degree 5. So let's see. First, I'm going to plug in n equals 1. And so if I do that, let's see, I have negative 1 to the 0 times negative 2x to the first power divided by 1. Next up, if I plug in n equals 2, we have negative 1 to the first power, negative 2x squared divided by 2. Next up, I have negative 1. Again, we need to reduce this by 1, so it goes 2 there. And then negative 2x being cubed. And we have a few more of these to go. Remember, we can see kind of that this is going to be x cubed right here, that we have an x being cubed, and we want to go up to degree 5. So, okay, I know that this is not the most exciting thing ever. That's okay. Sometimes not exciting problems are, excellent ones to put on quizzes and exams. You don't want every problem to be exciting. All right, and here we have something raised to the 5th power there. And so let's maybe go ahead and take a line to simplify here. This is just going to be negative 2x for this first bit. And then let's see, we have minus from this here. Let's see, negative 2 squared is going to be 4. So we're going to have 4x squared, but we need to divide that by 2. So in fact, this can be simplified down to a 2 there. Here we have, let's see, a couple negative 1s, and then we have 3 of these negative 2s. So it actually is going to be negative there. And let's see what we're going to have, negative 8x cubed divided by 3. That one we didn't get any nice cancellation, but that's fine. Here we have negative, and we're going to have 16x to the 4th divided by 4. So this does simplify a bit, and we could write it as 4. And then here we're going to have negative 32x to the 5th divided by 5. So again, this would go on forever if you wanted the full series. But in this case, we just want the polynomial stopping after degree 5. And so this right here would be my final answer. One more here. This one's a little bit tricky. So 3 to the x. Well, looking up above and seeing right what we have at our disposal, the only thing that really stands much of a chance here, right, the only exponential on this list is e. And so I'm going to do a little bit of a trick here, and I'm going to rewrite 3 to the x as e to the natural log of 3 times x. So normally it'd say, why on earth would you do this, right? I mean, it's much simpler to go like this way, right? And of course, you could use the power rule for natural logs and all that sort of stuff to see that these are indeed the same. But here you can actually see that we have a reason to make things more complicated because we have a series expansion already for e. So I'm going to take this bit right here, and this is going to be my u. And I'm going to substitute that in here, right? E to the u is going to be equal to all of this stuff. And so let's go ahead and do that. So substituting that in. So this is going to be equal to summing up from n equals 0 to infinity of u, which is my natural log of 3 times x raised to the n divided by n factorial. And remember, we only want the first 5 terms, really, for this. So we're going to just do a 5th degree Taylor polynomial. And so, well, first we need to plug in 0. So we're going to have, well, anything to the 0th power is going to be 1 divided by 0 factorial. Ooh, this is a good challenge question here. Does anyone remember what 0 factorial is equal to? Yeah, 0 factorial is indeed equal to 1. And so this is just kind of like a good continuation definition here. So 0 factorial is equal to 1. Next up, if we go ahead and we plug in n equals 1 everywhere, we're going to have the natural log of 3 times x divided by 1. After that, we're going to have the natural log of 3 being squared times x squared divided by 2 factorial. 2 factorial is the same thing as 2. Then we're going to have the natural log of 3 being cubed next to x cubed divided by 3 factorial, which is 6. So trying to simplify kind of as we go this time. Natural log of 3, plugging in now 4 everywhere I see an n. So x to the 4th divided by 4 factorial, that's going to be 24. And lastly, the natural log of 3 raised to the 5th power times x to the 5th divided by 5 factorial, which is 120. So this right here would be the 5th degree Taylor polynomial for this particular series. All right, so I'm sure there are some questions. Let me go ahead and highlight this too, so that this is my final answer. Well, you can see these ones where you can read it right from the table are not so bad, all things considered. Let's go ahead. Ian, you have a question.
Hi, can you hear me?
Yeah, sure can.
All right, so this might be a bad question. I know it says in the direction, it says to the degree of 5, but is there a special reason why any other special reason why we're doing it up to 5? I was just curious.
No, it's just I wanted to do enough or a high enough degree so that way you could kind of see the pattern.
Oh, okay, thank you.
But yeah, maybe you could argue that some folks could really see the pattern after 3 or something like this. And so maybe 5 was a bit overkill.
Oh, okay, gotcha.
Good. Any other questions? Any questions in the Q&A? I haven't popped this open.
No.
Not right now. Okay, one more question here.
All right, so my question was, when should we be weary as when n starts? For example, most of this n starts at 0, but when should we check to make sure that n starts at 0?
All the time. I mean, so I guess the only one here where it doesn't start at 0 is right when it's given n equals 1 for the natural log 1. But I mean, you should always read and make sure.
All right.
I'm not sure, like, besides that, there's no other way to like, I mean, you should always check the table, I guess. Don't just kind of go too fast sort of deal. But that's how I would check, is go to the table.
So if it was like not 0, could we like make it 0 by making n minus 1, for example, if n is equal to 1 to make it start from 0?
Yeah, you could re-index in order to make it start at 0 all the time if you'd like to.
All right, thanks so much.
Yeah, definitely. Okay, so let's go ahead here. And so yeah, this is the nicest case scenario. Now we need to talk about the less nice case scenarios here. And that is sometimes, even though we have quite a bit with this, we still don't have a great way, you know, for every single function out there to use this table, right? There's just going to be some functions that don't fit on this table that you need to do something else. And so here's an example of one right here, example 8, where if you go back to this table of all of the ones that are given to us, you'll see that nothing really exactly lines up for a square root function, right? And so whenever that happens, we do have to go back to the definition. And so remember, in the pre-class videos, we were given this definition. This is for a Maclaurin series, or another way of saying that is a Taylor series centered about x equals 0. Sometimes also, by the way, they'll use a equals 0, just because in a lot of the formulas, right, you have an a, and that's just really emphasizing that you're plugging in 0 for a there. And so this right here is the definition for the Maclaurin series, or the Taylor series at 0. And you can see this is a truncated definition. I didn't go through all of the hypotheses here. I just said if your function is nice. So long as it's well-defined and you can take derivatives and all that sort of stuff. So, okay, well, in this case, if we would like the Taylor polynomial of degree 3, notice we're going to need quite a few derivatives. We're going to need all of this stuff right here. After that, you'll have a 4th degree and a 5th degree and so on and so forth. And it does continue on forever if you want to have the Taylor series. But if you're just interested in a Taylor polynomial, right, then you stop where it tells you to stop. And so, okay, well, let's go ahead and plug in 0 here. And basically, we're just kind of collecting pieces right now, right? We know that we need f of 0. We know that we need f prime of 0. We know that we need f double prime of 0. And we know that we need the 3rd derivative at 0, right? Because these are the only kind of mysterious things for this formula. Once I have those, I'll be able to just plug them in, and that'll be the Taylor polynomial. So, okay, f of 0. So here's my function. If I was to plug in 0, I would have the square root of 4, which is 2. Okay, not so bad. Next up, I need to start taking some derivatives. So let me kind of maybe go off to the side here and give myself some space to take derivatives. So I'm going to say f of x. And for the purposes of taking derivatives, remember, it's really nice to write this in its exponential form, right? So x plus 4 raised to the 1/2 power. And so now if I want to take one derivative here, the 1/2 will come down. I'll reduce my power by 1. And then I'll need to use the chain rule, multiply by the derivative of the inside. But luckily on the inside, the derivative is just 1. Let's maybe preemptively also get our 2nd and 3rd derivative going here. So the 2nd derivative, 1/2's along for the ride. When I take the derivative, now the power comes down. And we reduce our power by 1. So this goes from -1/2 to -3/2. and a third derivative. So we have the 1/2. In fact, let's simplify this down. We're going to have -1/4. And then when we take the derivative, -3/2 comes down, right? That's the power now. And we reduce our power by 1. So it goes from -3/2 to -5/2. And now we'd like to plug in 0 into all of these things. So I'm going to have 1/2. And let's see, when I plug in 0, this is going to be 4 to the -1/2 power. But let's see, this can simplify a little bit, right? Because when you have a negative exponent there, this is the same thing as division. So we could put that in the denominator. And when you have the 1/2 power, remember, this is the same thing as the square root. So we could write this as the square root. And so after all is said and done, this is going to be 1/4. All right, how about the next one for the second derivative? Well, when we have our second derivative, we have our equation over here. We have this coefficient of -1/4. And when I go and I plug in 0, I'm going to have 4 raised to the -3/2. So -1/4. Again, we have a negative exponent. So this is the same thing as division. We have the 1/2 power. So that's going to be the same thing as the square root. We already said that the square root of 4 is going to be 2. But now don't forget, this isn't just -1/2 power, right? There's that 3. And so we still need to cube this. So you kind of just break up your exponents and you consider it piece by piece. So I did the negative, I did the 1/2, I did the cube, right? So I just do all of these things one by one sort of deal. So this is going to be what, 1/8, and then we have this 4. So this is going to be -1/32, I believe. Last one here, let's see, we have +3/8. And we're going to have 4 raised to the -5/2 power. So again, the fact that it's negative, I'm going to push it into the denominator. The fact that there's a half power there, that means there's going to be a square root. So the square root of 4 is 2. And so I guess I need to know what 2 to the 5th power is. 2 to the 5th power. Well, maybe computer scientists out there have all your powers of 2 down. This is going to be 32. Yeah, and then we need to multiply that by 3 more 2's, right? That's going to be our 8 there. So we need really 2 to the 8th power. And yeah, this is 256. Or of course, we just have right, our TI-30s. So you can, of course, use that as well. Okay, so you can see this is a little bit more painful, right? Because when you don't have the nice formulas from the previous page, right, you have to go through and you actually have to calculate out all of these derivatives. Now that we have all these things, we're going to take them and plug them into our formula here. So we're going to have 2 plus 1/4 x plus the second derivative here is going to be -1/32. And we need to divide that by 2 factorial times x squared. And then finally, we have our 3/256 divided by 3 factorial times x cubed. And this is going to be our 3rd degree Taylor polynomial right here. Let's go ahead and take one line to simplify it, and then we'll take some questions here. So 2 plus 1/4 x minus 1/64 x squared and plus 1/512 x cubed. So this is with it all being simplified down. And a fun thing to do, maybe after class or maybe just in a new window or something like that, is to graph, just like we did before class, graph the function itself and graph the Taylor polynomial and see that this Taylor polynomial does a good job of copying our original function, especially around x equals 0. So that's maybe a nice way to kind of see visually what have we accomplished with all of this calculus and algebra and kind of it just feels like there's a lot of manipulation and it's hard to see necessarily what we're doing. So I would advise that take this and graph the two like we did before class with e to the x, and that can be quite useful. Okay, a couple of questions. Gabriel, you had your hand up. What's going on?
Yes, I just have too many questions. So like to represent like a Taylor like polynomial, like before, isn't it just like t sub 3 of x?
Yes. Yeah. So this, if I wanted to, I didn't write the name down here. Maybe I should have. This is the Taylor polynomial of degree 3.
Okay, and then the second like little question I had was if we wanted to represent this as a series, because at the top it says the sum of from n equals 0 to infinity of f to the nth power of 0 over. So like for this one, for example, would it just be like f to the third of 0 over 3 factorial x to the n, or how would we write it?
So we'll have some examples like this moving forward, but in general, right, you would have to figure out a formula of how to represent the nth derivative. So, right, we have maybe you could say that the function itself is the 0th derivative, and then you have the first derivative, and then you have the second derivative and the third derivative. And the question is, well, how do you represent in general, right? If I said, what is going to be the 100th derivative, something like this, it'd be a real pain to take 100 of these things. So you need to figure out a general formula for what does the nth derivative look like. And so you can see that there's some pattern going on here, right? That there is something certainly that we could maybe do in order to create this nth derivative, but this one's actually pretty challenging.
Okay, thank you.
Yeah, no problem. Okay, and maybe one more. No, the other hand went down. That's fine. Okay, any questions in the Q&A?
Yeah. Have you said something like what a nice function is?
Yeah, so this is me I wanted to kind of truncate this definition. And so where is it here? I guess in the textbook and whatnot, which is where these notes came from, it just says if f has a power series expansion at A, which basically just means that it needs to be, you need to be able to take lots and lots of derivatives of this thing. So that's really what I mean by a nice function, is that you can take lots of derivatives and they all exist and make sense. If at any point, right, you can't take derivatives, so kind of like you remember maybe back in our Calc 1 days, if you try to take the derivative of the absolute value of x at 0, well, it's not differentiable there, right? And so you get undefined. And then what do you make as your coefficient? And so long as you can actually take not only one derivative, but 2 derivatives and 3 derivatives and 5 derivatives and all that sort of stuff, so long as you can take lots of derivatives, right, you're going to be able to create a power series. Otherwise, you may not be able to. So there are horrible functions out there, and this is just the fancy words to kind of exclude those horrible functions. Let's do another one here. So here we have find the power series representation in sigma notation for Cinch, right? So here's one where we actually want to figure out the full, sigma notation and everything for Cinch, and we're going to be doing it about 0 here. And so again, kind of if you go back to the sheet before this, right, there is we didn't give a rule or anything for hyperbolic sine, right? So it's not on that table. And so we have to go and we have to use now this definition right here in order to come up with the series expansion for hyperbolic sine. And so, okay, again, kind of our overall goal here is going to be, since we want to write this in sigma notation, we're going to be looking at this one. And so a lot of these things are already, fine and everything. The only thing is, right, we don't know what maybe the nth derivative for this function at 0 looks like. And so let's go ahead and maybe start writing this down a little bit here. So we need to figure out what is the nth derivative for our function at 0. So we'd like to come up with a formula for this. And so, okay, well, let's take a running start at this, right? So I'm going to go ahead and figure out just what is f of 0 and what is f prime of 0, f double prime of 0, right? We're going to just try to calculate out a few of these things in order to hopefully discover what the pattern is. And then once we have that pattern, maybe we can write down the nth derivative at 0 here. And so, okay, well, if we were to just take the function itself, which is hyperbolic sine, and we were to plug in 0. Anyone remember what is hyperbolic sine of 0? Yeah, exactly. It actually lines up quite nicely with regular old sine, right? So this is just going to be 0. Now, the derivative of hyperbolic sine is hyperbolic cosine. So notice that one's pretty easy. I'm not even going to take a separate space to calculate out the derivative there. So, and then we need to plug in 0 into this, the derivative. Hyperbolic cosine, when you plug in 0, you get 1. Okay, let's keep going. When you take the derivative again, you're going to get hyperbolic sine. Plug in 0, you get 0. Next up, hyperbolic cosine. Plug in 0, you get out 1. So this is actually quite interesting, right? It looks like sometimes, well, actually in a lot of the cases, we have zeros. And then there's these other cases, right, where you have kind of the odd number of derivatives, you get out 1s. So if I was to maybe write this out, because we need something that alternates 0, 1, 0, 1. So I guess formally, if you wanted to write this down, you would say the nth derivative at 0 takes on 2 things. It's either 0 if you have an even number of derivatives. So if n is even, or it's going to be 1 if n is odd. So this is one of these piecewise defined functions here. And so maybe this isn't, a super beautiful answer. So why don't we go ahead and actually write out a few terms and we can find a nice series expansion for this, with the sigma notation and everything. And so, okay. So we're going to have 0 plus 1 over 1 factorial times x plus 0 over 2 factorial x squared plus 1 over 3 factorial times x cubed. And if we wanted to do a few more, right, the next one's going to be 0. And maybe after that, we'll also go up to x to the 5th here. So 1 divided by 5 factorial x to the 5th. So notice that these zeros are going to be taking out all of our even terms. And all we're going to have is just our odd terms. Now remember, this is actually very similar, right, for our regular old sine here. Right, with our regular old sine, we just have the odd terms and no evens. And so if you want to write something down that just has odd terms and not any evens, well, I would write down exactly this. So let's go ahead and do that really quick. So I'm going to be summing up from n equals 0 and beyond. And if I just want the odd terms, right, it's x to odd powers, and I'm dividing by the odd factorials, so 2n plus 1 factorial. And remember, with regular old sine, it alternates. It goes plus, minus, so on and so forth. But here with our hyperbolic sine, you can see actually that it doesn't alternate, right? So we have just a bunch of positives being added together. So we're going to forget about that alternating piece here. And let's be a little bit paranoid, right? We could double check. You plug in n equals 0, n equals 1, n equals 2. And you can see that indeed you get just the odd powers, and it lines up exactly with what we have here. So this is a way to kind of exclude the fact that you have all of these zeros when you have evens. So my final answer here is just this. And you can see maybe yet again here, why hyperbolic sine has the notation that it does, that it's, it's good friends with regular old sine. All right, so let's go ahead and take a question here. Aditya, you have the floor.
Hi.
Hi.
So when in web work or like on quizzes or exams, so if it asks for the first 5 terms of the series,
Yeah.
What would that be? Would that include the zeros to the x, or like the coefficient of the first 5-degree polynomial? Would
A
that
lot of
zeros, or like is it just?
A lot of the times I've seen in web work, it specifies the first 5 non-zero terms. So it would exclude the 0 terms. If it doesn't specify like that, and if it just says what's the 5th degree, Taylor polynomial or something like this, centered about whatever, in this case 0, then you would write, just this. I mean, you can not write the pieces that are zeros if you'd like, but then you can see you would only have 3 terms that are non-zero, right? 1, 2, 3.
Right. Okay.
Okay. Super. Good. Any questions in the Q&A, Yuan?
Why is over 2n plus 1 factorial, not n factorial?
Yeah, so we wanted to make sure that we only had odd factorials down here. Likewise, our power of x needs to be odd. So notice that this is not 2 factorial, right? It's 3 factorial. It's an odd number. And likewise here, 5 factorial and 5 sort of deal. So we want to make sure that we're excluding all of the evens and only getting odds. And so the 2n plus 1 just makes sure that we're getting only the odd pieces. If you had n factorial, then you would go, well, 1 factorial, 2 factorial, 3 factorial, so on and so forth. Good. All right. And so this is maybe the second case scenario where, again, kind of these functions, they don't line up with anything that we have in our table. And so we need to go out and find the Maclaurin series and the Maclaurin polynomial for these. The final case here is if you're given a Taylor series that isn't centered about 0. So if it's not a Maclaurin series, those rules that we have up there, sadly, are useless. They don't work for it, and you need to create your own. So for instance, I would like to do example 10 here, where we have xe to the x. Now notice you have seen this before. Xe to the x we saw up here, and we figured out the Maclaurin series that is centered about 0 for this one right here. And remember, it was very, very fast. And so one would hope, right, that this would be very fast. After all, it's the exact same function. We're just kind of offsetting it, right? Instead of centering about 0, we're centered about 1. Sadly, though, even though it's a nice thing to hope for, right? Sadly, it does not work out. So you do need to kind of take your time and create this using this definition for the Taylor series. And so we'll get this and we'll look at it kind of back and we'll see that, yes, there are some major differences here. So, okay, again, let's see, we want to do the full-on Taylor series, and we'd like to do the radius of convergence as well for this one. So, okay, well, the full-on Taylor series, right, we're going to want this bit right here, doing the sigma notation. Of course, we'll get a running start here, but our end goal is going to be to figure out what is the nth derivative of our function at 1. So maybe we'll do just the function at 1. We'll do the first derivative at 1. We'll do the second derivative at 1. Hopefully by then we'll see the pattern. If not, maybe we can interject one more here. So let's go ahead and maybe do the first derivative at 1. So sorry, just the function at 1. So if I plug in 1, I'm going to have 1 times e to the 1. Okay, well, that's just e. All right, now for the first derivative at 1, well, we need to go ahead and calculate out our first derivative. So let's spend some time calculating out some derivatives here. Let's just do 2 of them for the time being, right, corresponding to these 2. If we need more, we can do more. So when I take the derivative here, remember that this is a product of 2 functions. So whenever you take the derivative of a product of 2 functions, well, you have to use the product rule. So it goes the derivative of the first times the second plus the first times the derivative of the second. Thinking about that I'm going to have to take another derivative, let me kind of simplify this down a little bit just by factoring. So I'm going to write this as x plus 1 times e to the x. So I factored out my e to the x from both of these. Okay, let's take a second derivative. So if I take a second derivative again, well, I need to take the derivative of this, and still we see that there's a power rule going on. Or sorry, not a power rule, a product rule going on. So, okay, product rule, we take the derivative of the first times the second plus the first times the derivative of the second. And if I was to simplify this down a little bit, let's see, both of these terms have an e to the x, so I'm going to go ahead and factor that out. And I'm going to be left with 1 plus x plus 1. Of course, we should probably combine the like terms, and so we're going to have x plus 2. And so, okay, now we're ready to probably plug in, right, 1 everywhere we see in x. So if I plug in 1 everywhere I see an x, well, let's do it first to our first derivative here. We're going to have 2 times e to the first power, or that's going to be 2e. Okay, how about for our second derivative here? If I plug in 1 everywhere I see an x, I'm going to have 3 times e to the first power. Or that's going to be the same thing as 3e. So my question is, from this right here, what's the pattern? Right? If I took 0 derivatives, I had just e. If I took 1 derivative, I have 2 e's. If I took 2 derivatives, I have 3 e's. How about if I take n derivatives? How many e's am I going to have? And so, yeah, I do see a lot of n times e coming up in chat. And this is very close to correct. But notice here, when I took 2 derivatives, I don't have 2e. And likewise, when I took 1 derivative, I don't have 1e. It seems to be that I always have 1 more than the number of derivatives that I took. And so, yes, if I'm going to be taking n derivatives, well, then I need 1 more e. So n plus 1 times e. So this right here is the general formula for the nth derivative of our function at 1. And so if you want the Taylor polynomial centered at 1 here for x e to the x, then in sigma notation, this goes from n equals 0 to infinity. And remember, I'm going to be copying down just exactly what this says here. We have the nth derivative at 1 divided by n factorial times x minus a raised to the nth power. So remember, my a is 1 in all of these cases. So we just figured out our formula. This is going to be n plus 1 times e divided by n factorial. That's all the coefficient stuff. That's the bits that doesn't have any x's. And then here we have all the bits with x's, right? X minus 1 raised to the nth power. And of course, if you wanted to, see exactly what this Taylor series is looking like, right, you would just start plugging in n equals 0, n equals 1, n equals 2, right? And you would get all of these pieces here. So this right here would be my final answer for the Taylor series for this thing centered at 1. Again, I want to compare this with my original answer back here. So my original answer for when we were centering at about 0, notice that this is significantly different, right? So we had x to the n plus first power, 1 divided by n factorial, right? This came very, very fast when you're centering at about 0. This one, on the other hand, right, it does look significantly different. And so it's very hard in general to kind of, even if you know what it looks like centered at 0, to somehow get this here, right, to get the centered at 1 power series. And so do be careful with that, right? Anytime you have a center other than 0, don't use the items on that table. They won't be useful. Okay, let's, one last thing here, right? Right, it says use the series to find the radius of convergence. And so maybe in the interest of time, I'll just say that the radius of convergence is going to be infinity for this. And in order to figure that out, you'll use the ratio test. So just like anytime you have a series and you want to know what the radius of convergence is, right, you always use that ratio test. This n factorial in the bottom there is kind of the giveaway that the radius of convergence is going to be 0. Sorry, the radius of convergence is going to be infinite. There. Sorry for the misspeak. Okay. Well, let's see. It is already 2:40, so this is going to be our last problem for today. I'm sure there are questions because this is a complicated topic. So please, anyone with questions, please voice them.
There's one asking why you center around another number. Why it's necessary?
Why it's necessary to center it around another number. Maybe, so you could argue that for these Taylor series that have an infinite radius of convergence, that it's not as necessary in as many situations. But still, there will be times where you want to, especially in the 1111, the section coming up, where you want to maybe approximate with your Taylor series and figure out how far you're off by. And so in particular, if I was interested in approximating, you know, this x e to the x at like 1.1, right? Now that 1.1 is considerably closer to 1 than it is to 0. And so I'm going to get a much better approximation by using the power series centered at 1 to approximate at 1.1, rather than using the power series centered at 0. So that one's kind of far enough away that you're going to get a significantly worse approximation. And then the other case is when you don't have, you know, a very large radius of convergence. So for instance, one of these in the earlier, maybe this natural log of 1 plus u, centered at 0, right, you only have a radius of convergence of 1. But if you're interested in calculating out or approximating, again, maybe like the natural log of 100 or something like this, notice you can't plug in 100 to this because it's outside of your radius of convergence. So it's just going to diverge. And so it may be that you need to center it about some other value in order to get, you know, a power series that you can actually plug in something like, you know, 100 into it. Good questions. Will, you have the floor.
Yeah, I had a question about the second to last problem we did.
Yes.
Where it alternated for only odd numbers.
Oh yeah.
Yeah. It doesn't like line up because you're multiplying it by 2. I was just wondering why that is. Like for example, if you were to plug in 3, you'd have x to the 7th over 7 factorial.
Mm-hmm. Yeah, I just didn't write that one out, right? So that would be the next one.
Oh, okay. So then the 0th term is then going to be what was previously the first term.
Yeah, so these ones where you have some missing pieces like this, notice this is going to be like the, to some extent, this is like the 0th odd number here when you have 2n plus 1. And then this is going to be the first odd number, right? When you plug in 1, you're going to get the 3 out. And then this is going to be, so yeah, it's not, these are not the, yeah, the wording has to be specially crafted, you know, especially for like web work and stuff like this, for like your C sub n's. So quite often I've seen in web work, right, that you have C sub, you know, 2n plus 1, you know, x to the 2n plus 1. Yeah. So it may ask for a formula for this, in which case you would say, well, that's going to be 1 over 2n plus 1 factorial. But yeah, you're right. It's tricky. You can't really ask for C sub n anymore, right? Because otherwise you need to have this weird function over here that is sometimes 0 and is sometimes 1.
Right, because the middle, the terms in between still exist. They're just 0, right?
Yeah, they still exist in the same way that you can always add 0 whenever you'd like to things.
Right, okay.
So whether or not you actually add 0 to things, right? No one will ever know if you do or don't.
All right, thank you.
Yeah, definitely.